Herzlich willkommen, Professor Dr. Patrick Noack, zu unserer Uni. Und jetzt, wir starten die Präsentation von Dr. Noack. Die Worte ist für Sie.
Ja, vielen Dank für die Einführung, Fabio. Ich werde die Präsentation heute in englischer Sprache abhalten, weil der Vortrag auch in Englisch ist und insofern stelle ich das Ganze jetzt um. So I want to talk about chances and challenges of machine control and guidance systems for digital agriculture applications today. As mentioned before, my name is Patrick Noack. I'm working for the University of Applied Science in Weinstefan-Triesdorf, which is in Germany in the center of Europe. And I'm the head of the Competence Center for Digital Agriculture here. So I want to give you a brief overview on the chances and challenges on the one hand and on the other hand. Well, the chances we have when it comes to digitalization is that the costs for sensors, for data storage, and for data processing have been decreasing over the last decade and over the last years and are still decreasing. And that is a big chance we're going to see that later. The accuracy and the resolution of sensors at the same time, they're not only getting cheaper, but they're also getting much more accurate and they have a high resolution. So this is another chance. We have got increased connectivity, not necessarily in Germany. I think the 5G coverage in Brazil is probably even better than the one in Germany, but it's increasing and we've got new technologies like Sigfox and other technologies as well. We see that with image processing and near-infrared spectroscopy, especially when combined with machine learning or artificial intelligence, that it offers new opportunities. And that we have got, at least in most of the countries, an existing yield gap. So we don't have the maximum of yield at the moment. We still have got opportunities to improve. On the other hand, we've got opportunities. And unfortunately, I only see the Portuguese text here. So I'm trying to look, okay. So now we come to the challenges. As I understand, some of you have got an agricultural background or are studying agriculture. So we've got basically a lot of societal challenges, at least in Europe, and I understand that also in other parts of the world, we've got decreasing workforces. So we don't have enough people who work in agriculture. We've got different environmental issues when it comes to pollution, and other issues as well, such as biodiversity. We're going to dive into that later. And we've got a changing consumer demand. At the same time, we've got legal issues and liability issues. We've got a problem, I think, with modular approaches and standards. A lot of companies are building systems which are a closed shop. So they're building solutions which don't properly talk to one another. And last but not least, we've got a very important thing is that we need to catch up with the users, with the farmers, in order to explain to them what the return of investment for them is if they invest into digital technology. We've got issues with resilience, validity, and quality, which means that not all the digital systems we're using at the moment are working properly. And with remote service diagnostic, and last but not least, with the user experience, so the graphical user interface, so the software we are using, or man-machine interfaces. Well, let's have a look at Maslow's hierarchy of need, which you may have heard of, and this is basically a hierarchy of what we need as people. And this is actually a small joke I'm always making. Some people claim that the most important thing is Wi-Fi, and then comes survival, safety, love and belonging, esteem, and self-actualization. But this is not actually the case. Actually, it should look like this. We've got, in the first instance, we've got physiological needs. And if we look at the physiological needs, this is food, it's feed for our animals, it's bioenergy, and it's raw materials. And this is all provided by agriculture. So agricultural production is basically, or covers most of the basic needs which human beings have. So we're not covering something which has got to do with self-actualization, with self-esteem, with love or belonging. It's about really the basic needs which we have as humans. This is very important because sometimes people say, okay, if agriculture causes such a lot of issues, or we've got such a lot of problems with it, why don't we simply stop doing agriculture? And this is simply not an option. Yeah, let's look at the world population, how this has been growing. I think we're all aware of this big number that we're going to be 10 billion people by 2050. If you look on the graph on the left-hand side, you see that the amount of people living on Earth was pretty stable around 300 million or 500 million people until basically the 17th century, and then we see that the population is growing, and only recently, since 1900, the world population has been growing dramatically. Yeah, this is a fun fact. On the right-hand side, you see the growth of bacteria, which is, well, basically has got a similar form to growth if you look at this and this at this side here. But please be reminded that this is hours and this is basically years or centuries. But it seems that at the moment we are growing like bacteria on planet Earth. So the summary for me is that the world population has increased by a factor of 4 over the last 100 years. So if we look at the arable land which we've got on Earth, that is stable apart from a steppe which we've got here. But I think this is rather a statistical issue. We see that the arable land which we've got on Earth has been more or less stable since 1990, so there's no additional land which becomes available for agricultural food production. If we look at arable land in Europe, it has even decreased. So since 1960, in Europe, we've lost 11% of the arable land. If we look at Germany, we've even lost 14%. I don't know the numbers for Brazil, but it's probably going to be similar, that the amount of arable land is not necessarily increasing. Yeah, employees. I said that we don't have enough people working in agriculture, so this is percent of total employment in agriculture worldwide, which has decreased from 43% to, well, approximately 27% since 1990. So this is the last 35 years, or this is a range in overall of 25 years. So we've lost 39% of the people over 25 years working in agriculture. If we look at that in Europe, it has even further gone down from 7.5% to 3% of total employment. And if we look at Germany, it looks even worse. We used to have more than 4% of people working in agriculture, and at the moment it's less than 1.5%. Meaning that we've lost approximately 70% of the workforce in Germany. Yeah, this is also something which supports this trend. This is the number of seasonal workers in Germany between 2010 and 2016, and we can clearly see that the number of seasonal workers has decreased. Yeah, and not very astonishing, we see at the same time that the farm sizes are increasing. we see that only the number of farms with an acreage of more than 100 or 200 hectares are growing, and that the smaller farms, which are smaller than 100 hectares, that they are decreasing in number. So we see basically something which we call structural change, that the bigger farms are increasing, so farms are getting bigger and bigger, and the smaller farms are decreasing. Yeah, if we look at that in a summary, we've got larger farms and we've got less employees. And if we've got less people working on larger farms, we're basically losing knowledge about single fields. And thus we have more demand for data and information, because the knowledge is not there traditional. It has not been given from the father to the son, but the knowledge is basically gone because the farms have been growing and some fields have been going in and we don't have any prior knowledge about it. Yeah, if we look at environmental issues, this is a nitrate level in Germany. So we've got a nitrate level of 50 milligrams of nitrate per liter, which is a maximum allowance per law for drinking water. And we see that this is already exceeded in most of Germany, or in pretty big parts of Germany, which are marked red here. And the problem with this is that this is mainly caused by agricultural production, so by over-fertilization. So this is one of the environmental issues I've been mentioning earlier. We've got too much nitrate in the groundwater, and we need to do something about that. Yeah, this is a maximum amount of fertilizer, or this is the amount of fertilizer we would be required to reduce if we wanted to reach a level of 37.5 milligrams per liter to be on the safe side. And what we can see here is that there are some areas in Germany where we would be allowed to fertilize at all in order to reach this aim. So at the moment, Germany, when it comes to nitrate in groundwater, we're in a pretty serious situation. Yeah, then we've got a lot of discussions in the European Union and especially in Germany about agrochemicals. This is one example about glyphosate potentially killing honeybees. I'm pretty much, well, I would think that you've got probably similar discussions in Brazil as well. So we basically have got the demand to reduce the amount of agrochemicals in agricultural production. Yeah, then we've got climate change. I keep having this example here. So in Germany, in the year 2018, between March and September, when the plants are usually growing in our region, we only had 0 to 25% of the long-term average precipitation. This doesn't happen every year, but it happens every now and then. It can hardly be predicted, but it's definitely something we need to react to. Okay, normally, from my knowledge, what usually was a solution when we had, for example, issues with workforces, not enough people always said, let's build bigger machinery. But at the moment, I've got the feeling that we've already reached the limits with respect to length, width, and height. We've got legal constraints in Germany, and they're already reached. And we also have got application constraints. We don't want too much weight on the road, or we're not allowed to use very heavy vehicles on the road. And in the field, very heavy vehicles lead to soil compaction. And on the other side, we've got application constraints when it comes to the distribution of straw, fertilizer, and agrochemicals. So simply making machinery bigger is, at the moment, not a solution in agriculture, not anymore. was a solution for the last decades, but I think it's not going to be a solution in the future. Yeah, so let's make an intermediate conclusion. Why did I tell you all this, or how can we summarize this? So agricultural production covers basic human needs: food, feed, bioenergy, and raw materials. So it's nothing we can replace. It's primary production. We can't change anything about that. And it's not that we only have to produce a certain amount of food. The demand for food is growing as the world population is growing. At the same time, the area of arable land is stable or even decreasing. So what would I normally do if I've got a growing population? I would simply say, okay, let's use more arable land in order to produce more. But unfortunately, the amount of arable land is limited and cannot be increased. The amount of people involved in agricultural production is decreasing. So this is one asset, one important asset we're using is people, and this asset is decreasing. At the same time, we are being asked to adapt to environmental and societal challenges, which basically means reduce the reduction of agrochemicals, the reduction of fertilizer on the one hand, in order to handle the nitrate influx into the groundwater, and on the other hand, to reduce the negative effect of agrochemicals on the biodiversity. And last but not least, the size of machinery has reached its limit with respect to size and weight. So how can we summarize this? We can summarize this by saying we need to increase the production on existing area with less input of labor and material. And this is a big challenge because we need to produce more without having more area, but with less people and less inputs, right? So we need a strategy for that. We need to do something about it. So what could be a potential solution? So the options we have, the solution would be to basically increase the productivity by increasing yield and making more out of existing labor force and material input. So we will need to increase the efficiency of production. And there are several ways to do that. So one option is to improve breeding, for example, by genome editing like CRISPR-Cas. We can reduce the meat consumption or replace meat by cultured meat or in vitro meat. And one other option would be to introduce more autonomous or intelligent system into agricultural production. I'm always saying that because I think using digital tools or digitalization can be one tool in order to increase efficiency. But I'm trying to take away the burden from digitalization to be the only solution in order to solve the problems we have in agriculture. Okay, so can we improve yields? There's an interesting site which is called yieldgap.org, and there you can see how much of the potential yield is still open to be reached. And if we look at Denmark up here, they obviously have already reached 88% of the production capacity, and they only have a yield gap of 12%. Looking at Germany, we still can do better. We could still increase by 22%, France by 27%, Austria by 39%, and Spain already by 53%. If I look at Tunisia, they've got a potential of 82%. So that's something we also always should look at. We can only increase efficiency if we've not already reached the limit of yield. And it seems that in most parts of the world, we've not yet reached the limit, and there's still potential for growth. Yeah, then people tell me, yeah, if I want to work with digitalization, that's also expensive. And I always say, no, it's not. And then they say, I've got to buy all this software and all these programs. And then I say, no, let's take a look at the software which is available. So the first thing I really need to mention is that we've got a couple of really good operating systems, starting off with Linux, which is an open source and cost-free operating system. When it comes to robot, some of you may have heard about ROS. It's a robot operating system. It's also free of charge. Everybody can download it if he wants to develop robots. If we talk about programming languages, Java and Python are two powerful languages, and the most development environments you can download are free of charge. Then if we look at software which you can basically process data, there's KNIME, there's YASP, there's R, OpenCV, and QGIS, for example, a very powerful geographic information system, and they are all free of charge. And if I look at software for databases, PostgreSQL, MySQL, or Hadoop, just to name a couple of them, this is also completely free of charge. So if people tell me that they need software in order to do digital projects and the software is too expensive, I would say, no, it's not. It's free of charge. You can just download it. Then people say, oh, okay, the software is free of charge, but I need some data. And if you look at this is just a tiny, small bit of examples where you can get open and free data from satellite image to RTK correction data, over weather data, statistical data from the FAO, or also ISRIC, for example, the World Soil Information System. There's hundreds, if not thousands, of data sources related to agriculture, which are out there with data which just needs to be downloaded. And yeah, I would just encourage you to look at that because I think there's more data than we've already made use for. Yeah, accuracy. So this is data from a GPS receiver about 35 years ago, and the receiver had an accuracy of approximately 100 meters. It was a Cell Globos LN 2000, which probably was 50,000 euros or something. So a receiver with an accuracy of 100 meters was 50,000 euros. If we look at the prices, 1994, an RTK GPS receiver had a price of 50,000 euros. And if I look at an RTK receiver today, for example, the Mublox Neo here, or lately the F9P, such a receiver is 200 euros or a little bit more, probably 250. So the prices for RTK GNSS receivers, which give us accurate position, have dramatically dropped over the last 25 or 30 years, so that the cost for sensors is not something we should be bothered with. For those you don't need RTK accuracy, so 2.5 centimeters, if you can live with 5 to 10 meters accuracy, there's also GPS receivers available for €6.79 or for €3.65. Computers used to be very expensive. I just want to give you an overview. If you look at Raspberry Pis, this is not the latest price. They may be at 60 euros at the moment. But if you look at Arduinos or even ESPs, they're very powerful devices. You can write software in Python or in C++ for them, can do an awful lot of things. And as shown here, the prices range between €1.50 and €30. So if somebody tells me the computer he needs in order to automate a certain process are too expensive, I wouldn't support that. And my favorite controller is a smartphone. I've taken this one here because at that stage it was only €85. I've got a controller here inside. I've got a telemetry system. I can send and receive data. I've got an IMU. I've got a GPS receiver and a user interface for €85. So it's incredible what we have. And all those who say that digitalization is too expensive, I can just tell them, no, it's not. We already have things like this in our pocket. And basically, we don't need to pay anything for that. Yeah, if we talk about aerial images, operating an aeroplane used to be about €50,000 per year in order to make aerial images. And if we look at drones today, you've got an average price of €1,000 or €1,500 for which you can get a drone. So acquiring aerial images not only once per year, but basically daily or weekly is not very expensive. So that has become very cheap as well. Yeah, good cameras, which you can install anywhere to capture videos or pictures, are ridiculously inexpensive. Yeah, this is basically an example from a bachelor thesis where we're looking at wear analysis or Analyse de Desgaste. So we're trying to find out how this share, which is shown here, metal piece, which is used for soil cultivation, how this is degrading over time. And we basically took a couple of pictures and used these pictures in order to make 3D models. And again, we were using free of charge software here in order to understand which materials can we use in order to make soil cultivation more sustainable. Yeah, this is a 3D model of a parcel plot trial, which you can create with a drone. What we normally do is that we deduce the height, which is marked here in blue, which would be the soil, from the red heights, and then we automatically get a measurement of the plant height. And the plant height, often I talked about breeding, is an important measure in breeding processes. Yeah, connectivity, we talked about telemetry systems. So the ideal system is that I've got a tractor on the right-hand side with an EaseOfIT terminal, which is communicating with an implement. I've got GNSS and I'm connected to a cloud system where I can log yield, nutrients, and task data. I have soil data and weather data available in this cloud, and through an expert system, I'm feeding back the optimal treatments, and they go back to the terminal, which then send the information to the implement. Yeah, talking about 5G networks and new technology, I guess you have that available in Brazil as well. And as I mentioned, the coverage in Germany is not too good with 5G at the moment, but it gives us basically a very high communication speed of up to 10 gigabytes per second, low latency, and allows for 1 million participants per square kilometer to communicate with one another. Yeah, let's look at the LTE coverage. So I'm talking about 4G at the moment. What I saw was in 2018 that South Korea was the absolute leader when it came to LTE coverage. On place number 10 was the Czech Republic. And I found it funny that Germany is only on place 70, just behind Albania, which is a very, very, very small country in Europe. You can look it up where it is. It's in the mountains, but obviously the LTE coverage is even better than the German coverage. Yeah, this is LTE availability in Germany. You see, as soon as we come into bigger cities, we've got a pretty good coverage. but as soon as we come to the rural areas marked in red, we've got a very weak signal. Yeah, and then I learned something which is really a fun fact. What does 65% of LTE coverage mean? That it refers to the amount of people, or to 65% of the population. And I've been trying for myself in a GIS to optimize this. If I wanted to cover 65% of the population in Germany, I would have to cover the area marked in green here, and I could leave the other area completely uncovered, and I would still have 65% of the population with LTE. If I go up to 90%, it would look like this, and if I go up to 99%, it looks like this. Unfortunately, this area up here, which is now not covered by LTE, is one of the strongest agricultural production areas in Germany. So unfortunately, even if we cover 99% of the people with LTE, it doesn't help us with agriculture. Yeah, so I think what we need when it comes to mobile networks is coverage. That, at least in Germany, that's the most important thing. And then bandwidth, and then latency. So how long does the signal take from A to B? I mean, at the moment, what we see is that we've got a lot of internet-based communication, Starlink and others. And I think this can be very helpful for agriculture in order to cover the data access in rural areas. Yeah, and here I want to talk about the three-tier agriculture. It's not many people stick to that. It's basically a concept which comes from information technology or software development. You're trying to build different layers. One is sensors or data. The other one is logic or control, and the third one is user interface. And it makes absolute sense to stick to this three-tier architecture because if we talk about the user interface, if we want to use, for example, if we want to make a user interface in a different language, it's very easy to switch this block with another block so that we probably have a user interface in Portuguese or in English. And at the same time, if I'm using ultrasonic sensors from, for example, manufacturer A, and manufacturer A doesn't have them available anymore, I can exchange the sensors by those of another manufacturer, but the logic and the control and the user interface will stay the same. Yeah, then graphical user interfaces. This is at the bottom, you can see the user interface of QGIS, so a geographic information system I'm working quite a lot with. I mean, I personally like QGIS a lot and I work a lot with it, but I think that this user interface is not very user-friendly. And I see a lot of people struggling with that. I think things could be done better. And if you look at the user interface like this, this looks much better structured and easier to use. So sometimes I think it's not only about building an artificial intelligence or building a new algorithm or using a new sensor. I think one important thing is to make up user interfaces in such a way that people accept them and that they're easy to use. Yeah, I've got a video in here, which I think I can't show at the moment. Oh yeah, I can show it. So this is a drone which is controlled by a gesture. So somebody is holding his arm, and by the movement of his arm, he's forcing the drone or controlling the drone to turn around him. And I think this is a pretty cool way of man-machine interface. And I think that in agriculture, there's quite some potential to probably use gestures for drones or autonomous robots in order to interface with them, rather than having a tablet with some sort of weird user interface and a lot of menus and submenus. So that would be an alternative to what we've seen previously. Yeah, speech control is also something I'm very much into. I mean, we all know that from our smartphones, but I think in agriculture, this is not adapted quite a lot because we can easily adapt to different languages if we've got speech control. And also in agriculture, we often don't have our hands free, and we probably want to control something or we want to input an information. So basically, speech control is something which you think about as basically an alternative to click interfaces on tablets or laptops. Yeah, and then there's this one thing which is called user context analysis, which I found very interesting. I had the opportunity to talk to a couple of people who are involved in basically car manufacturing, and these people think about it a lot. They think, what does the man-machine interface, so a user interface on a tablet or a switch or a knob or a joystick, what is the best thing how I can interface with the machine? And there's a couple of things we should look at: the lighting conditions, vibration, noise, temperature, socio-ethical background, age, skill, role, and task. And as I said before, I think it's not only important to develop new models on your algorithms, on your sensors, but to think how can we manage to make people easier interact with digital solutions? Yeah, here's, for example, one thing about user interfaces. On the right-hand side, you can see the cabin of a tractor. And basically, we had this eye tracking glass, and we gave people a certain task to operate the front hitch, or I think it was the rear hitch on a tractor. And then we analyzed where people looked at, where they were trying to find the knob or the switch in order to actuate the hydraulics in the back. And it was very interesting that people looked at different places, so they were expecting the man-machine interface in different positions. And yeah, as I said, I think many of these situations in tractor cabins, they've been developed by engineers, so these are engineering solutions, and they don't necessarily match with the expectations of the users. Yeah, and then we can have probably different roles as well. We can have workers, group leaders, and CEOs. They could all use the same sensors and the same data and the same logical control, but they can look at the data from a different perspective. Yeah, but I think it's also important that different logics and controls have got an interface. And what I've seen quite a lot is that we've got several GPS receivers on one tractor for different functionalities, like a steering system, section control, variable rate control, or data loggers. And I think it's important to make interfaces in such a way that we've got only one GPS receiver, and this, in the form of an open architecture, distributes the position data which is providing to different systems. Yeah, and we've got a lot of barriers at the moment when it comes to interfaces. We've got data coming in, for example, from different combine harvesters with yield data. We've got soil data, nutrient data. They need to be processed into maps, and these need to go into expert systems. They need to create an application map, which needs to be transferred to different terminals. And every time I've got an interface, which is marked in blue here, I either have a proprietary standard or I've got an open standard, an open interface. And at the moment, we are fighting a lot with these interfaces that not every system can talk to one another. So that's stopping us at the moment from making digitalization easy. There are a lot of interfaces or standards we could use. Here are a couple of them. There are a lot more. So I just wanted to encourage you, if you are involved in some sort of data exchange between systems, before trying to invent a new data format, please look up whether there's an existing standard. Yeah, and then we talk about the system of systems. It may be that not getting back. It seems I'm stuck here anyway. So intermediate conclusion is that we've got massive amounts of data which is freely available. We've got very cheap sensors. We've got low-cost hardware. And we've got wireless networks for exchanging data. Standards are existing. And well, we probably have a little demand for further interface standards. But the most important thing is how we can derive relevant information from this data. So let's talk a little bit about multivariate data. What we've got quite a lot is, for example, cameras which deliver RGB images or even multispectral or hyperspectral images. So we've got a reflectance in different wavelengths. We're not only taking one picture, for example, of a plant or an animal, but we're taking one at different points in time. These on the right-hand side, this is microphone data or MEMS data, which we can do a fast Fourier transform on, and then we've got different frequencies with different, well, basically loudness levels. And as you can see, there are many frequencies and many different loudness levels. And this may all be related to a certain state of a machine or to a yield or nutrient efficiency. Yeah, so we've got multivariate data. For example, here, this is hyperspectral data from different corn varieties, which also shows that we basically see a clear difference between the varieties. Yeah, this is sound-based. Here we've got a chopping drum, and we were trying to find out whether the chopping drum was working good or not. And these are the frequencies or the amplitudes at different frequency levels. Yeah, special thing is near-infrared spectroscopy, which, as I said, does not only take the light from blue to green to red, but also in the near-infrared, so that we're getting a lot of information. This is used in agriculture quite a lot in order to look at plants from a tractor, from a drone, from an aeroplane, from the satellite, in order to determine chlorophyll content or biomass, germination. It's used for feed and seed in the laboratory for determining dry matter or protein oil content. We're also looking at salts, organic matter, water content, or even at fertilizer, the nitrogen concentration of liquid manure. So NIRS applications are basically, well, in agriculture, have a pretty wide application. So let's look at some spectral data or multivariate data. This is a vegetation index, the NDVI, related to the yield at different dates. So this was the 19th of April, 28th of April, 3rd of May, and so on and so forth. And you see that at no point in time there's really a good correlation between the vegetation index and yield. So if we put all this data into artificial neuronal network which looks like this. Then we suddenly get a good picture, so we can very well estimate the yield from the NDVI data. But this only happens because we take all dates together, feed them into a neuronal network, and deduce the yield. Yeah, and there's a lot of methods. Artificial neuronal networks are one. We can use random tree classification, decision tree, and so on and so forth. So there's a big opportunity of different methods to be tried. Yeah, classically what we're doing at the moment in research is we are building a model, so a calculation model. We are collecting field data. Then we are validating the model. We're optimizing the model, and then we go back to the field. So this is a process which takes a very long time, and this is basically done by universities. And what we all see at the moment quite a lot is that Google and Amazon, but also BASF, Bayer, John Deere, Echo, Cargill, BayWa, and the big supermarkets, that they basically use data from all different kinds of sources, feed them into AI models, into the model application. This is much faster than doing traditional science. And this is a big criticism from my side at the moment. I think we've got an issue with quality assessment, transparency of methods. We're just getting black box results from AI systems. Yeah, and another thing is, which I'm daily experiencing, is you can train a lot of AI models, but if the data you're inputting into the systems is not properly maintained or cured, they're talking about data curation here, then the models won't help you. And people from CGIAR, they basically said here that they spend 60 to 80% of the time for basically making the data suitable for big data analysis. Yeah, and here I've brought you a little example. Basically, this is a yield map as well. And the yield is increasing with a symbol size. So we've got high yield here and low yield down here. But at the same time, you see numbers inside. And the numbers is basically related to the credibility of the data. So we basically try to give the data an attribute which says, can I trust this data or can I not trust this data? Yeah, as a summary, basically agriculture covers many important basic needs of human mankind and cannot be replaced. But we've got issues in the productivity and in the environmental and societal domain. We've got, on the other hand, digital systems like sensors, telemetry systems, image processing, near-infrared endoscopy, and artificial intelligence, which are not too expensive, they're affordable, and they're helpful tools which offer many chances to tackle some of the issues. Where are the core challenges at the moment? I think standardized and open interfaces are an issue, because what I wanted to say earlier is that I don't think that a single entity has got a solution. But if everybody is working on partial solutions, and we've got good interfaces between the solutions, then probably a couple of people can very well collaborate and better work on the solution of problems as a single entity. As I've also mentioned, I see quite some potential in the user interface and the man-machine interface design. I think we've got pretty good sensors at the moment already, but it's sometimes not very easy to work with the systems. And last but not least, we've got a lot of data. That's true. We've got a lot of bits and bytes, and basically all our hard disk drives are full with data, but it's important to look at how we can derive information from them, and artificial intelligence can probably help us to use that. Yeah, that was it from my side. I hope this was helpful for you. If anybody's got questions, you can probably discuss the slides and probably write a small summary. Probably you can tell me how you like this lecture, and you can also send me open questions, and I would try to answer them as soon as possible. But I would suggest that you probably have a group discussion and basically write some questions as a group, 5 to 10 questions, which I'd be happy to answer. Okay. Yeah, thanks a lot. Goodbye.
Thank you, Professor Patrick Noack. And am Ende, finally, I give your email for questions, and your presentation will be at März online after the edition process.
Okay. Ja, Fabio, wir können uns gerne duzen übrigens. Das würde mich sehr freuen.
Okay.
Du, ich weiß nicht genau, wie ihr das macht, aber wenn die Studenten, also wenn jetzt lauter einzelne E-Mails kommen, ist das doof. Ja? Aber wenn die sich hinterher nochmal zusammensetzen und sagen, das haben wir nicht verstanden und da würden wir noch gerne ein bisschen mehr dazu wissen und ich bekomme da ein paar Fragen von denen, dann kann ich die gerne beantworten. Ja?
Okay, und dann wunderbar, deine Präsentation auf Englisch gemacht habe, weil viele Wörter, wir nutzen auch die gleichen Worte in Englisch.
Okay.
Technical Sätze oder Technical Wörter sind gleich.
Okay, ja, das ist gut.
Und ich habe auch nicht über diese Sicherheit dieser 3 Tiere, auf Deutsch Tier ist Animal in Englisch.
Okay, ja, gut, das ist immer wieder erstaunlich.
Okay, wunderbar. Und dann, ich danke Ihnen und auch einladen Sie, wenn Sie in Brasilien kommen, dann besuchen uns.
Ja, das mache ich gerne. Alles klar.
Okay, und Professor Dominikus werden am März hier bei uns sein.
Ah ja, okay, sehr gut. Alles klar. Ja, dann eine gute Zeit und Feliz Navidad.
Ja, Feliz Natal auf Portugiesisch.
Ah, Feliz Natal.
Frohe Weihnacht auch, wir nutzen hier.
Okay, sehr gut.